Hello everyone and welcome back to the second part in this video series in which I go through step 1 questions from 2018. So last time we did question 1, this time we're going to have a look at question 2. So here's the beginning of the question and we see straight away it's all about logarithms. Okay, so now questions about logarithms in step papers tend to be among the easier ones, I would say, and the solutions tend to be a bit less lengthy than other topics, but you do have to understand logarithms, and I mean really understand the key concepts and know the key results. So let's quickly write out all of the things we know about logarithms. So the question says if x equals log b of c, we need to know what this means. Log base b of c, okay, we need to know that is essentially the answer to the question b to what power equals c. Okay, in other words, if x equals log base b of c, that is the same thing as saying that b to the power of x equals c. Okay, they are equivalent. That is what log is saying, and from that we can deduce some fairly straightforward results. The first of which is that a to the power of log base a of b equals b, which seems like a crazy result until you realize this is literally the definition of log. Okay, if you're baffled by this, that probably means you haven't grasped what a logarithm is. Okay, because this looks complicated, but it's actually communicating a very simple message, just the definition of a log. Log base a of b is that number which, when a is raised to it, gives b. Okay, literally the definition of a logarithm. From it we also get another quite easy result. Log base a of a equals 1. Why is this true? Simply because if we start with a, what power do we need to raise it to get a as a result? And the answer is simply 1. A to the power of 1 equals a. Therefore, by the definition of logarithm, log base a to the power of a equals 1. Okay, we've got a couple more results, so I'll just list them over here. One of them is that if we've got log base a of b to some power x, then we can bring the x to the front, okay, to get x log base a of b. Okay, why is that true? Well, I'll leave that as an exercise for you to prove, but as a hint, think about this. If b equals a to some power c, okay, then what happens when we raise that to the xth power? B to the x, that's going to equal, by index laws, a to the cx. Okay, so now try and have a fiddle around with that in your own time and see if you can deduce this this law. But in practice, all we do when we have an exponent in our logarithm, we just take it to the front. Okay, and the final thing that we should know about logarithms, which comes up time and time again, is that the log of a product equals the sum of the logarithms. Okay, so if we've got log base a of xy, we can decompose that into log base a of x plus log base a of y. Again, I'll leave it up to you to prove that, but essentially it comes from the idea that actually a to the x plus y is equal to a to the x, a to the y, and this is essentially the logarithmic way of expressing that algebraic index law. So, okay, we've got all of the information we need, so let's have a go at the question now. In fact, we've already done the very first part of the question. If x equals log base b of c, well, we've said that's equivalent to c equals b to the x. Okay, so let's write that out. X equals log base b of c is equivalent to c equals b to the x. Okay, now we've been asked to prove that this law, and this is maybe the last remaining basic logarithm law that I didn't state here because we're asked to prove it in the question. So you should already be familiar with this hopefully, but now we're asked to actually prove it. And the hint is, always in step, use what you've just proved. Okay, so well, let's write out the more difficult bit of the expression. So log base a of c over log base a of b. And what can we do? Well, they've literally kind of spout out that we should be using c equals b to the x. So let's substitute that in. So instead of c, I'm just going to write b to the x here. And now, one of the laws that we've written above is crying out to be used, right? B to the x. Let's bring the x to the front. So that equals x log base a of b over what's in the denominator, log base a of b. And then hopefully you see these just cancel, and that gives us x. But what we want is to show that this is equal to log base b of c. But remember, when c equals b to the x is exactly that, log base b of c. Okay, and so as required, and so we're done. We're done with the introductory part of the question. So let's give ourselves some more space and let's see the next part of the question. So the next part of the question says, given that, in quite an obscure fashion, given that pi squared is less than 10, we need to prove that 1 over log base 2 of pi plus 1 over log base 5 of pi is greater than 2. Okay, this can seem completely baffling when you see it at first. Okay, what on earth are these pi's doing here? But we're given that pi squared is less than 10. So really, and because we've got an inequality here, when we see these pi's, we should really be treating them kind of as root 10s, okay? And that's the key thing. If we think of this as root 10, which is 10 to the half, and the half can come to the front, then actually these log base 2 of pi and log base 5 of pi don't seem quite so daunting. But still, the fact that we've got 1 over a logarithm, I mean, what do we do with that? Okay, as I said earlier, invariably in STEP, you will need to use the previous part of the question. So here, we've just deduced this result. Okay, so let's see if we can try and use it. And, okay, we've got a something over something, but here we've got 1 over something. So if I'm going to use this result, I'm going to need this to be 1. Does that make sense? But when is log base a of c equal to 1? Well, actually we already know that from this result. Log base a of a equals 1. So let's set c equal to a, in the hope that this result will give us something nice. So what do we get then? Log base a of a, which is 1, over log base a of b equals log base b of, well, c has now become a. So we get this result, which you may have already seen before. This result simply tells us that if we've got 1 over log a to the b, log base a of b, then we can swap the base and the thing inside the logarithm and get rid of the reciprocal. Okay, so that gives us a way of manipulating these expressions so that we don't have reciprocals and logs, because they're not normally a nice combination. So let's do that. So let's write down the left-hand side of our expression that we're trying to show is greater than 2. So log base 2 of pi plus 1 over log base 5 of pi. What's that going to give us using this rule we just deduced? Well, essentially, get rid of the 1 over and swap the a and b. So that's going to give us log base pi of 2 plus log base pi of 5. Okay? Now, that doesn't look like an improvement, except remember, log base pi, we should actually think of it in terms of root 10. Okay? So log base pi normally is a no-go, but actually here it's okay, because we're given this expression. So now we've got the addition of 2 logs with the same base, so we can use the product rule. So this is just log base pi of 2 times 5, which is 10. And that's good, because we were expecting this 10 to come up. But now let's consider this. If I write, since log x is increasing, and I'm using that fact, I'll leave that as an exercise for you to show. I'm using that fact so that I can say, okay, if the thing inside the log decreases, then the log of that thing will also decrease. And all I want to do is to say basically that this is greater than log base pi of pi squared. Okay, because we're given that 10 is greater than pi squared here. And so actually I can say, let's actually make that explicit. And since pi squared is less than 10, we can replace 10 with pi squared, making this smaller, and therefore since log x is increasing, making this whole thing smaller. Okay? So now log base pi of pi squared, well that just equals bringing the exponent to the front, 2 log base pi of pi, but log base pi of pi is just 1. So 2 of it just equals 2. Okay, and therefore we've actually shown exactly what we wanted to show here. So I'm just going to say as required. And we are done with part 1 of the question. So now let's have a look at part 2, and let's use a separate sheet of paper now. Although we can always refer back to our rules if we need to. So now, part 2 doesn't look all that dissimilar. Let's have a look. Given that log base 2, that says, of pi over e is greater than 1/5, and given that e squared is less than 8, prove that log of pi, natural log of pi, is greater than 17/15. Okay, so as soon as I see log, and I'm seeing some e's as well, I'm immediately thinking, actually let's do natural log, let's do log base e. Okay, but how do we get into that form? At the moment we've got log of 2, how do we get into the natural log? How do we get into the natural log? Well, we actually know that from this. Okay, so when we have natural log of 2 of pi over e, let's write this out. So we've got natural log, log base 2 of pi over e. I can actually write that as log, sorry, let me bring this closer so we can see it. Sorry about this. Okay, so this is actually equal to log base e of pi over e over log base e of 2. Let's move that a bit closer, sorry. There, hopefully you can see it now. So log base 2 of pi over e equals log base e pi over e over log base e of 2. That's literally just using this rule where a is the base that I want, the desired base, so I'm using it, this equals this, this equals this. And so actually I'm just sort of forcing in my log base e, which is what I want. So obviously this, the way we write that in maths, the log base e is just a natural log ln. So natural log of pi over e equals natural log of 2. Okay, and that makes me a lot more comfortable because I'm trying to work with e's. Okay, and in fact, the desired inequality that I want to show, this lower bound of natural log of n, is using the natural log. So this is a good first step. And we're told that this is greater than 1/5. Okay, well, let's try and work with that. Let's discard this bit. Let's try and work with this, because this is got everything we want in it. It's got an inequality, it's got some natural logs. So let's see. Natural log of pi minus e, well, that can actually be written in this form, log pi minus log e, for the same reason that log of a plus log of b is log of ab. We've also got that log of a over b is log of a minus log of b. That's something that I'll leave for you to show. So we've got log of pi minus log of e over log of 2 is greater than 1/5. Okay, but now of course we can say, well, natural log of e is just 1. So actually we've got log of pi minus 1, okay, and that's this. And then we can say that's greater than 1/5 log 2, natural log of 2. Okay, makes sense? So let's bring this closer and take this further away. It's the most difficult bit of these videos. Okay, we're trying to show that the natural log of pi is greater than 17/15, but we are told that e squared is less than 8. So seeing as it's not that clear what to do next, let's work with that for a little bit. Okay, so e squared is less than 8. What does that tell us? What does that tell us in terms of logs? Well, we can take the log of both sides. So e squared is less than 8. That just gives us that 2 natural log of e is less than the natural log of 8. Okay, but simplifying that, that just tells me that, well, natural log of e is just 1, so 2 is less than natural log of 8 is natural log of 2 cubed, and that's the 3 natural log of 2. Okay, so actually straight away this gives us a nice inequality, which is that log of 2, a natural log of 2 is greater than 2/3. Okay, so that's nice. Let's try and use that now. So what have we got from here? We've got that natural log of pi, because remember that's what we want to actually find a lower bound for. So we've got natural log of pi. Well, that's greater than from here 1 plus 1/5 natural log of 2. But we've just found that natural log of 2 is greater than 2/3. Okay, so that's greater than 1 plus 1/5 times 2/3. Okay, and then the rest is pretty trivial. This, when you just expand out the fraction, equals 17/15 as required. Okay, so that's part 2. And let's quickly have a look at part 3 now. Part 3 says, given that e cubed is greater than 20 and pi squared is less than 10 and log base 10 of 2 is greater than 3/10, prove that log pi is less than 15/13. Okay, so now we've just found the lower bound of log pi. Now we're trying to find an upper bound of log pi. So let's have a go at that. Let's do it on the same sheet. I think that should be fine. Let me just fold this so we get some more room. And actually, this is quite enjoyable, I would say, because we've just found a lower bound of pi, now log pi. Now we're going to find an upper bound of log pi. And the difference between those two fractions, 15/13 and 17/15, is only about 0.02, I think. So it's actually, you know, we're making some progress towards approximating pi in a very strange way. So let's try and finish this off. The most complicated hint that we're given is this one. So I'm going to start with that. Log base 10 of 2. Okay, and again, I want to put this into natural logs. So I'm going to write that as log 2 over log 10. Exactly what we did up here. Okay, just force in that log e using our rule. And we're told that that is greater than 3/10. Okay, so we're just doing exactly the same as we did before. So what does that tell us? Just looking at this expression like we did last time. So that's just telling us that natural log of 2 is greater than 3/10 natural log of 10. Okay. But look, we're told again that, like we were earlier, that pi squared is less than 10. So let's do the same thing that we did before. We're bringing, this happens commonly in step questions, we're bringing what we did in part 1, bringing what we did in part 2, and putting it together to get this more difficult result in part 3. So that's greater than 3/10 log, natural log of pi squared. Okay, since pi squared is less than 10 and since log x is increasing. And then we get that this is obviously just 3/5, right? Because log of pi squared is 2 log of pi. And, oh sorry, 3/5 log pi. Yeah, because log of pi squared is just 2 log pi. So we have the denominator to get that. Now, like we did before, we get so far and then we realize, oh, I'm kind of stuck. So we have to use the third inequality here, which we haven't yet used, which is that e cubed is greater than 20. Let's see. So e cubed greater than 20. What does that tell us? Let's do what we did before. Take natural logs of both sides. So we get that 3 log base e, which is 3, is greater than, taking the natural log of this side, greater than log 20. Now last time we got log 10 and split it up into 2 and 5. Now we've got log 20. Let's try splitting it up again. So by the product rule with logs, we can write that as log 2 plus log 10. We could write log 10 in terms of log 2 plus log 5, but actually in this question, we don't have any 5s, but we do have some 10s. And we do, in fact, have some 2s as well. So let's keep it in this form. What does this tell us? Well, it tells us that 3 minus log 2, just taking this over here, is greater than log 10. Okay. But actually, we have log 10 already. We've already worked with log 10. We found out that this was greater than 2 log pi. Okay. So what does this tell us? 3 minus log 2 is greater than 2 log pi. We're not very interested in that so much. But if we take this over to this side, so 3 minus 2 log pi, that is obviously going to be greater than log 2. Okay, this is more what we were looking at, because we found that log 2 was greater than 3/5 log pi. Okay, so it's good now that we've got a log 2 on its own, because now we can combine those. So combining our inequalities, we've got 3 minus 2 log pi, because you need something to connect the work we've done here and the work we've done here. Does that make sense? The thing that connects them is the log 2. So 3 minus 2 log pi is greater than log 2 from this. But then from this, log 2 is greater than 3/5 log pi. Okay, so now that should be natural log of 2. Natural log of 2 connected the two inequalities, but now we can discard it because we've got what we want. We should be able to get from this some kind of bound on log pi. So this gives us that, well, 3 is greater than, in brackets, 2 plus 3/5 log pi. Okay, this equals, well, 13 over 5 log pi. I'm sure you can see where this is going. Final step, simply bringing this over here. We get that log pi is less than, over here, 15 over 13. Okay, as required. So that is the question done. So as you can see, it wasn't the longest question. If I just get the solution, where's the first page? Here it is. So here's the full solution. Okay, not the longest step solution ever. So basically 2 A4 pages, and not the most difficult mathematically either. All it required was a very good knowledge of these basic rules of logarithms, and quite a lot of pattern spotting, quite a lot of asking, okay, why did they ask me to prove this fairly trivial result? Probably so that I can use it again in a later question. Yeah. So the key to a lot of step questions actually is asking yourself, okay, I've done part A, now I'm stuck on part B. What did I do in part A? What can I learn? How can I apply it in part B? Hopefully that was helpful. There'll be a video up with question 3 coming out soon. Please do ask me if there are any maths competitions or maths problems or other step papers you'd like me to cover. But I hope that was useful. Good luck in your step revision and in your step exams and in your mathematical careers. Goodbye, see you soon.